Okay, we're back and we're computing the MLE for linear regression, for Gaussian linear regression with a known variance. And we have our data, we assume probabilistic model. We want to maximize the likelihood function, so we took our likelihood, we wrote down an expression for the likelihood function. And we simplified it, so we got this, and then we simplified this sum by observing that it was equal to just the norm of this thing squared, or the dot product of this vector y minus AW with itself, where A was this design matrix thing. And now, so let's rewrite that. Let's rewrite what we just found. So the probability of the data given theta equals, I'll just write this out, 1 over 2, this part isn't going to matter, 1 over 2 pi sigma squared to the n times e to the minus 1 over 2 pi sigma squared times y minus AW transpose times y minus AW. Right. So now to maximize this guy, that's what we want to do. So this, maximizing this is equivalent to minimizing this part here. You know, you could check that. You just, this part's the only part that depends on W. You know, you take the log. This is a constant, so that's not going to matter. You know, this is constant, so we can just, this doesn't matter. And the minus makes it going from maximizing to minimizing. So we want to minimize this. So in other words, our goal is to minimize, put it this way. So we want to minimize W or y minus AW transpose times y minus AW. Just the square of this norm. Want to minimize. Okay, so let's see what we can do with that. Now this is a nice linear algebra expression. This part's gonna involve some linear algebra, so if you aren't familiar with your linear algebra, you may want to brush up a little bit on it. So let's what we're going to do is the calculus thing. We're going to take the gradient, set it equal to 0, and then look at the Hessian, do all that stuff. So let's multiply this out. This is y transpose y minus 2 times y transpose AW, because, you know, we take y transpose times AW here, and AW transpose times y, that's a scalar, so we can transpose it and pull those together, plus this becomes W transpose A transpose times AW. Okay, so that's good. And now, to minimize this guy, we are going to take the gradient. So the gradient, with respect to W, to be precise, of this, let's call this, I don't know, let's give it a name. Let's just call it like, let's call it L or something. So the gradient of this thing equals, well, the gradient, you know, the derivative of this with respect to W is always 0. So we get minus 2 y transpose, let's see, what do we want here? This is, so the gradient, I guess we want to flip this first. So these can be, this can, maybe we should have written it this way. This is W transpose, because this is a scalar quantity. That's W transpose A transpose Y. Right? So that's equal to 2 times A transpose Y. So let's check that. That was a little trick there. Oh, and then there's more, but well, let me finish saying what I'm going to say here, and then we'll come back. Actually, let's divide this by 2 here. Sorry, I'm changing things up. That'll make things a little easier. We divide by 2, then this 2 goes away, because it doesn't matter. This is just a constant, so that doesn't affect the minimizer. Plus 1/2 here. Okay, so this 2 is gone. Minus, switch back to blue, minus A transpose Y. And now this is going to be A transpose A W. So let's check those. I just claimed that this gradient is equal to that, and let's verify that. So we'll just do a little calculation here. If we have a vector A times and the dot product with W, that's just the sum AI WI. And if we take the partial derivative with respect to WJ, say, then we just get AJ. So the gradient, remember the gradient of a function is just so for this function, for example, it's the column vector of these partial derivatives. So it's the column vector partial with respect to W1, partial with respect to W2, partial with respect to Wn if these are, n-dimensional or something. So this becomes it's just A, right? A1, A, N, and that's just A. So that means that proves this first claim here that so I guess I wrote it this way. So A in this case would be Y transpose A, or A transpose is equal to that, rather. And so A is A transpose Y. And that's exactly this. Now let's check the second claim. So if we have W transpose, let's say just BW for some generic matrix B, and we want to take the derivative of this with respect to WJ. This is what's called a oh right, well that's the partial, sorry. It's partial. This is called a quadratic form, and it's always equal to the sum over, let's make this K actually. I want to use IJ in the sum. Partial with respect to WK is the sum over all pairs I and J, and it's WI, WJ, and let's assume here, so let's assume B is symmetric. Makes things a little simpler. And in fact, this A transpose A is always symmetric, so that's fine. So we have this sum over all this is all I and J from 1 to N. And if you take the partial derivative of this with respect to WK, when I equals J, so when I and J are equal to K, you're going to get, it's going to be WK squared, and so you'll get 2 WK BKK when I equals J equals K, and when if neither of them equals K, then it's just 0, and if only one of them equals K, that occurs exactly twice. And by our assumption that B is symmetric, by the way, this Bij is the ijth entry of B. By our assumption that this is symmetric, then Bij equals Bji. So it always occurs twice for any given I. It always occurs twice that there is a factor Wi, Wk, Bik. So what do we get? So we get 2 times. Well, I'm not writing this quite right here. Sorry, so this is what I meant. So let's write it down here. Partial with respect to wk. So I'm going to move it through wi wj bij equals to wk bkk if, so we'll get rid of this. That was the first case. If I equals j equals k. And the other case is if only, well, if neither of them is equal to k, then it's 0. And if only one of them is equal to k, then it's like wi if j equals k and I is not equal to j. And so on. So, you can check the other cases also. And you find that since there's two of these, because bij is symmetric. Oh, sorry, I should have put bij. This becomes, it's just, well, I guess I should have put, let's see, so if I put I and ij here, that's the same thing. This is just a little calculation, but I wanted to make sure you see how to do it. There's two of these occur, and so we just get the sum over I from 1 to n of 2 times wi bik. And that's the same as bki, because b is symmetric. And so this is just 2 times the ith, so it's the ith row. So it's just 2 times the kth row of b, the inner product of that with w. So the gradient with respect to w of, you line all these partial derivatives up in a column, and that's just equal to 2 times bw. So that's just a little calculation. I wanted you to at least see roughly how it's done, and you can check that if you want. All right, so that means we take the gradient of this guy with respect to w. We get, so the 2 cancels the 1/2, and we just get A transpose AW, and that's this. Okay, so that's good. So that's the gradient. And now we want to set that, so we want to get the minimum of this function. This is thinking of it as a function of w. So let's set that gradient equal to 0. Oh, well, it's easy, right? We can just, if we set the gradient equal to 0, if that equals 0, then we get A transpose AW equals A transpose Y. And we want to solve this for W, so we can, to find it, well, at least a critical point. So here's a little aside. So we want to invert this A transpose AW. We'd like to do this, right? We'd like to say W equals A transpose A inverse times A transpose Y. But we need, of course, we need A transpose A to be invertible. So it turns out that it's under some mild conditions it is. So let's stop there. We'll check those conditions, and we will take the Hessian also and verify that this critical point is indeed a minimum in the next video. So all right, we're getting close now. We're hot on the trail. So we'll be back in a minute.